So what if you could take any shape you can imagine, a circle, a triangle, you name it, and translate it into pure numbers? Well, that's the absolute magic of coordinate geometry. It's basically a language that turns pictures into algebra. And today, we're going to learn how to speak it.
You know, this quote right here just gets straight to the point. Think about it. Before this whole idea came along, geometry and algebra were kind of like two totally different worlds. But coordinate geometry, it built the bridge between them. All of a sudden, a visual problem could be solved with the pure, clean logic of an equation. That's the huge leap we're exploring today.
So let's reframe this for a second. This isn't just another math lesson. It's like you're getting a new superpower. Seriously. It's the ability to look at the world around you and actually see the numerical code that's running everything underneath. It's that moment where just seeing something becomes solving it.
So where do we even begin with this? Well, every map needs a grid, right? Some kind of frame of reference. For coordinate geometry, that grid is the coordinate plane. You can think of it as the canvas where all our shapes and lines are about to come to life as numbers.
And honestly, the core idea is almost ridiculously simple. Just picture a treasure map. You start at one spot, the big X on the map. Every single other point is just a set of directions from there. Go 3 paces right, that's your X value. Go 4 paces up, that's your Y value. And just like that, every single point in space has its own unique address. Okay, so let's give our map its proper official names. That horizontal line that goes left and right, that's the X-axis. The vertical one, up and down, is the Y-axis. And that super important starting point right smack in the middle, we call that the origin, and its address is 0, 0. Every single location is measured from this one spot. It's the foundation for, well, everything.
All right, so we've got our map. Now we need a toolkit to actually start exploring it. Turns out there are 3 essential tools that let us measure and analyze anything on this plane. This is where the real work, the translation from shapes to numbers, really begins.
This feels like the most basic question you could ask, doesn't it? If I'm standing at point A and I want to get to point B, just how far is it? I mean, we could pull out a ruler, but that's the old way of doing things. What we want is to calculate the distance with perfect precision using only their number addresses, their coordinates.
And here is the really clever part. That straight line you see between 2 points, it's actually the long side, the hypotenuse, of a right-angled triangle, a triangle that's been hiding there in plain sight the whole time. The horizontal distance is one side, the vertical distance is the other, and the line we actually want to measure is what connects them. Now, if you remember a squared plus b squared equals c squared from school, this formula should look pretty familiar. It's literally just Pythagoras' theorem wearing a disguise. The change in x, that's your a, the change in y is your b, and the distance we're looking for is c. It's a perfect example of an ancient geometry rule finding a brand new home in algebra.
Great, so we can measure a line. Awesome. But what if we want to find its exact center? Where is the halfway point on that journey from point A to point B?
And believe it or not, the solution here is beautifully, wonderfully simple. If you want the middle of the whole line, you just have to find the middle of its horizontal part and the middle of its vertical part. In other words, you just average the x-coordinates and then you average the y-coordinates. That's it. And here's what that looks like as a nice, clean formula. You add the x's and divide by 2, then you add the y's and divide by 2. Bam! That gives you the exact coordinates of the midpoint. So elegant and so effective.
Okay, tool number 3. We can measure a line's length and we can find its center. But what about its personality? Its steepness. Are we talking about a gentle, rolling hill or a sheer cliff face? We need a way to measure that, and that's the third tool in our kit, slope. The classic way to think about this is rise over run. Just imagine you're climbing a staircase. For every single step you take forward, that's the run. How much do you go up? That's the rise. That simple little ratio, rise divided by run, gives us one powerful number that describes the entire steepness of the line.
And the formula, of course, is a direct translation of that idea. The rise is just the change in the y values, right? And the run is just the change in the x values. You divide one by the other, and you get m, the slope. Just one number that tells you the entire story of that line's direction. And that single number tells you so much, instantly. Is the slope positive? The line is climbing up. Is it negative? It's falling down. A slope of 0? You're on perfectly flat ground. But what about a vertical line, like a straight cliff face? Well, the run is 0, and as you know, you can't divide by 0 in math. So we just say its slope is undefined.
It is literally off the charts. So we have our toolkit: distance, midpoint, and slope. Now let's put it all together. Because with these three tools, we can write the unique code for any straight line in the entire universe, its equation. And it turns out there's a simple three-step recipe for this. First, you find the slope. Second, you take that slope and any single point from the line, and you plug it into this handy template here, the point-slope form. From there, you just tidy it up, and you've created the final equation. It's a rule that every single point on that infinite line has to follow. Now usually, you'll want to simplify that equation into this incredibly useful format, y equals mx plus c. This is the famous slope-intercept form, and it's so popular because it basically tells you the line's two biggest secrets at a single glance. M is its slope, and c tells you the exact spot where it crosses that vertical y-axis. So, what's the big payoff for doing all this work? Well, it's this. We can now describe visual relationships using simple algebraic rules. Let's see what this code we've learned can tell us about two of the most basic relationships in all of geometry: parallel and perpendicular lines. And right here is where the true power of this system just becomes undeniable. How can you tell if two lines are ever going to meet? You just check their code. If their slopes are identical, they are parallel lines, forever. And how do you know if two lines cross at a perfect 90-degree angle? Well, their slopes have this weird, beautiful relationship. When you multiply them together, they equal exactly -1. A visual question answered with simple multiplication. Amazing. So we have this incredible toolkit, right? We can find distances, locate midpoints, and decode the equation of any line. But now, let's just zoom out for a second and remember the big picture, why this was such a revolutionary, game-changing idea in the first place. It all comes down to this single insight. We're no longer stuck with what we can physically draw with a compass or measure with a ruler. We can now unleash the full, unlimited power of algebra on problems about shapes and space. This was the moment that two giant fields of mathematics finally merged, and it opened the door to solving problems that were completely unthinkable before. So just look at this question. A little while ago, this might have looked kind of intimidating, right? But now, you have every single tool you need to solve this, right now. You know how to find a slope, you know the special rule for a perpendicular line, and you have a point to anchor it all in space. The geometry has been translated, it's just an algebra puzzle now. So what's your first step? You know that feeling when you're staring at some crazy math equation and just wish you could see the picture it's trying to paint? Well, today, that's exactly what we're going to do. We're turning those equations into simple pictures. And trust me, this isn't about making art. It's about gaining a visual superpower that'll let you solve really tricky problems in just a few seconds. All right, look at this thing. How would you even start to graph it? The old-fashioned way? Plotting points one by one? Ugh. What if I told you there's a way to see the final picture instantly without doing a single calculation? That's the puzzle we're going to solve today, and it's the superpower you're about to learn. So, here we go, our graphical puzzle. I know, that equation looks like a real monster, right? It's got negatives, parentheses, exponents, a lot of moving parts. But it's actually hiding a really simple secret. And by the end of this, you and I are going to crack it wide open together. Now, to crack any puzzle, you first need to understand the code. So we're going to rewind just a little bit, go back to the absolute basics for a moment, just to make sure we're all on the same page and have a solid foundation to build on. Okay, so let's get the official textbook definition out of the way. A graph is just a set of points where for every x you plug in, the function spits out exactly one y. It's all very precise, but honestly, that's a little dry. Let's think about it a different way. Let's call this the 5th grade explanation, because it's that simple. A graph is nothing more than a picture of a rule. That's it. You pick a number for x, you apply the rule to get y, and you plot that little dot. You do that over and over and over again, and poof, a picture emerges from the dots. Simple, right? Okay, now this is where the magic really begins. Here's the secret. You do not need to memorize a million different graphs. It turns out that almost every complex graph you'll ever see is just a tweaked version of one of 3 super simple blueprint shapes. Blueprint number 1, the line. You see an equation that looks like y equals mx plus c, you know, without a doubt, its picture is a straight line. The m just tells you how steep it is, and the c tells you where it starts. That's it, done.
Next up, our old friend, the quadratic. The instant you see an x squared in an equation, you should think one thing: a U-shaped curve. We call it a parabola. It can be wide, it can be skinny, it can be right side up or upside down, but the basic shape is always that U.
And our final blueprint, the exponential. I like to call this one the swoosh. It's that shape that starts out kind of flat and then just takes off for the sky, getting steeper and steeper super fast. This is the shape of everything from money growing in a bank to populations exploding.
Okay, so we have our three blueprints: the line, the U, and the swoosh. Now it's time for the master key. This is the big idea that unlocks everything else. From now on, we are not going to draw new graphs from scratch. We're just going to take our basic blueprints and transform them.
Let's start with the easiest one, moving up and down. If you take any function at all and just add or subtract a number on the outside of it, the whole graph just slides straight up or down. If you add 3, it goes up 3. If you subtract 5, it goes down 5. It's exactly what you'd expect.
Now, what about moving side to side? Well, that happens when you add or subtract a number inside the function, right next to the x. But here's the one tricky part, and you gotta remember this. It's the opposite of what you'd think. Seeing x minus 2 actually moves the graph to the right, and x plus 2 moves it to the left. Yeah, I know, it's a little weird.
And that weird little rule brings us to the single most important takeaway of this entire explainer. If you remember only one thing, make it this: anything happening inside the parentheses with the x moves the graph sideways and it's backwards. Anything happening outside the function moves it up and down, and it's normal. That's it. That is the secret code we've been looking for.
Okay, but what about flipping things? What if we want to turn our U-shape upside down? Well, that's easy too. You just stick a negative sign on the outside of the whole function, it acts like a mirror on the x-axis, and the entire graph just flips over.
So here it all is, all in one place. This is your transformation cheat sheet. You can see adding outside moves it up, subtracting inside moves it right, and a negative outside flips it. And see that last one, vertical stretch? That's what happens if you multiply the whole function by a number. It just makes the graph taller and skinnier. This table is your new best friend. All right, we have the blueprint shapes, we have the transformation rules, we have everything we need. It's time. Let's go back to that monster equation from the beginning and solve this puzzle once and for all. Okay, here's our equation again. The first step is to ignore all the extra numbers and just find the blueprint. What's the core shape here? Well, I see that little squared symbol, and that screams quadratic. So we start with the most basic U shape there is, y equals x squared, sitting right at the center of the graph. Step 2, we look inside the parentheses. We see x minus 2. Okay, inside affects sideways, and it's backwards. So minus 2 doesn't mean left. It means we slide the whole U shape 2 spots to the right. Step 3, let's deal with that big negative sign out front. That's an outside change, so it affects the graph vertically. It's our reflection rule. So we take our U shape and we just flip it upside down. Boom! And now for the final piece of the puzzle. That plus 3 just hanging out at the end. That's an outside change, so it's a simple vertical move. We take our upside down U shape and we just lift the whole thing straight up by 3. And look at that, it's the exact picture of our equation. Puzzle solved, and we didn't have to plot a single point. Now you might be thinking, okay, that's a cool party trick, but it is so much more than that. What you've just learned is a genuine mathematical superpower. It's a completely different way of thinking that lets you solve really hard problems just by looking at them. It's going to save you so much time.
I mean it. When you're taking an exam, this is pure gold. By quickly sketching a graph, you can instantly see the highest or lowest point. You can find out how many answers an equation has just by seeing how many times two graphs cross. It's a visual shortcut that gets you straight to the answer. Let me show you. Take a look at this nasty-looking problem. How many solutions does this have? Trying to solve that with algebra would be an absolute nightmare. But with our new superpower, we just draw the pictures. We sketch the swoosh shape of e to the x, we draw the straight line of 3x, and we can clearly see they cross in 2 spots. That means there are 2 solutions. Done. It took seconds.
So what's the big takeaway here? You haven't just learned a bunch of rules for moving shapes around on a grid. You've actually learned a new language. You've learned how to look at an equation and read the story it's telling you. A story of shifts and flips and stretches. And that, my friends, is a whole new way of seeing the world of math.